section in Chapter 11 is 11.4. It is on effusion and diffusion of gases, which are two words that I confuse all the time myself, and so I always have to look up the definitions of them. But here's what we have. Diffusion is when two gases are mixing together. So this is an example of diffusion. So there's some perfume in this bottle. I'm assuming perfume or something else. Perfume. It's perfume. And now they're removing the lid on that perfume. Well, that smell is going to spread out across the room. As it spreads out across the room, what it's actually doing is it's mixing with the other gases that are around it. So notice this is a molecule of the perfume. This is the nitrogen in the air, maybe some oxygen in the air. So what this is diffusion. That gas is diffusing. And as it goes further and further out, it is actually going to get more and more diffuse, I suppose we could say, as it goes further and further out. Now, if we want to calculate the rates at which those gas molecules move out, well, we could measure their root mean square velocity. We had that equation before when we were looking at kinetic, like a theory. I believe the velocity is like 3RT over the molar mass. If we wanted to get its velocity, typically we don't calculate the velocity of an individual gas. Well, we could. It's not that we don't. But more often what's useful for us is to look at the rates and compare the rates at which things diffuse. So notice, if we want to do that, we can say that the kinetic energy of any gas is 1/2 mv squared. So that's the kinetic energy of the gas. Again, that is really, temperature is a measure of the average kinetic energy of any gas. So if we take the kinetic energy being 1/2 mv squared, just like we have it here, and if we have two gases, notice, at the same temperature, well, then they both have to have the same amount of energy. So if we have two gases, same temperature, they have to have the same amount of energy. So we can set this 1/2 mv squared equation equal to another 1/2 mv squared equation. So now what we can do is we're going to get rid of the 1/2, since 1/2 is on each side. Multiply both sides by 2, we get rid of the 1/2. And so now we have a different relation. Mass times the velocity squared equals mass of the other gas times velocity squared. Again, this is for the two gases if they're at the same temperature. Now notice, if we rearrange this equation, we can get the velocity of A over the velocity of B equals the molar mass of A over the molar mass of B. So again, these big M's are always molar mass when we're looking at this calculation. It's not the mass of an individual molecule, it's the molar mass that we'll use for them. Now notice what they do is they take the square root of each side, that cancels out the squares, and then we have the square root on that side. So we can say the comparison of the velocity of the gases is going to be based upon the square root of the molar masses. So that's typically how we're going to use this. If we want to compare the rates of effusion, or the speeds at which the gases mix, I suppose we could say, that's not really the correct term, but if we look at the rates of their effusion, the rate of one gas over the rate of another, notice this is where the equation looks like it's kind of flipped. So if we want the rate of A over B, we have to take the square root of molar mass of B over the square root of molar mass A. Not really that terribly tricky. We just have to know how to interpret it. Again, this relationship is actually for effusion. And what effusion is, again, a little bit different than diffusion. It's not one gas spreading out into another. What it is gas moving across a barrier, the rate at which a gas will move across a barrier. So notice if we have onions in a bag, some of that smell of those onions will diffuse. They'll actually move through the barrier, because the barrier, even though it's plastic, it's not completely, it's not impermeable. It is permeable, not impermeable, so the gas molecules can move through. Again, there's very small holes in the plastic, none that we can possibly see with our own eyes, but small enough for molecules to move through over time. Okay. So simply, diffusion, again, is one gas moving out into the world, expanding itself. The other one, effusion, is a gas moving across a certain barrier. Now notice this is going to use that equation we said. Estimate the molar mass of a gas that effuses 1.6 times the effusion rate of carbon dioxide. So we are looking at something. Now notice we have this funny equation. Let's see, how do we use it? So we have the rate of A over the rate of B is equal to the molar mass of B over the square root of the molar mass of A. So that's our equation. So we're saying a gas effuses at a rate 1.6 the times of carbon dioxide. So that would be 1.6 over 1. So gas A is 1.6 times faster than gas B, and gas B in this case we are saying is our carbon dioxide. So I take the square root of the molar mass of carbon is 12, dioxygen 2 times 16, so my molar mass is 44. So the square root of 44 over the square root of the molar mass of A, which is essentially what we're looking for. Now, just like anything else we do in our gas laws, there is some algebra involved. Easy enough, though. I'm going to bring this molar mass of A over to the other side, so it's on top. Square root of molar mass of A is going to be equal to the square root of 44. Now I'm going to put 1.6 on the bottom on the other side to clear it. So if that goes to the top, the 1.6 can go to the bottom. Now, if you don't follow my algebra, I apologize. I'm not really much of an algebra teacher. Hopefully, you can rearrange equation. That's my hope. Now, notice we can just do this calculation, and then notice at the end we'll have to take the square of it. So we want the molar mass of A, not the square root of the molar mass of A. So let me do that here. If I take the square here, that will cancel that. Square of here will cancel. I also have to take the square of what's on the bottom. So we have 44 divided by 1.6 squared. My molar mass is going to equal about 17.2. And again, it's in grams per mole. Now we could try to figure out what this gas is. Just because I've spent too much time in a chemistry book, I have a good guesstimate of the gas. Probably ammonia gas, because we have a nitrogen, which is 14, and 3 hydrogens each, which are 1 each, and that would give us a mass of about 17. So if I had to guesstimate what gas we were talking about, it would be ammonia gas. This question isn't asking that, it's just asking you estimate the molar mass, and we did that. We estimated the molar mass. This question will be funner. This gas will be funner. Number 3, list the following gases in order of increasing average molecular velocity. Okay, so if we say the kinetic energy of a gas is 1/2 mv squared, and at the same temperature, the mass, the 1/2 mv squared of one gas has to equal the 1/2 mv squared of another gas, say this is B, well then what that's saying is if this gas is moving faster, right? So this gas is moving faster. Say this gas is moving slower. Well, what does that say about their masses? Well, if this one is moving faster than this one, well, then this one has to have a smaller mass than this one, okay? Because those two terms have to be equal. So, which makes sense, right? A smaller gas will move faster, a heavier gas will move slower, but they'll still have the same amount of energy, because energy, again, is a function of the mass times the velocity. So we want to put them in order of increasing average molecular velocity. Well, what does that mean? That means we want to put them in order of increasing velocity, which means we want to put them in order of decreasing mass. So our slowest gas there, well, let's look up the molar masses of them. So water is oxygen plus hydrogen is 18 grams per mole. Helium is 4. Hydrochloric acid would be 1 plus 35, about 36.5 grams per mole. Bromium fluoride, now here's what I'm guessing my winner is. It is 98.9, so that is the clear heaviest gas. So clearly it's going to be the slowest. And then nitrogen dioxide, perhaps this will be my second slowest because I have 2 oxygens. So that would be 2 times 16. We have 32 plus 14. 32 plus 14 is what? 46. Okay, so there we go. So my slowest gas is going to be the heaviest. And if I put them in order of increasing velocity, well, nitrogen dioxide would be next, followed by hydrochloric acid, followed by water, and then helium, because helium is my lightest. So what this is telling us is a gas like helium will diffuse or effuse much, much faster than a gas like bromium fluoride because it moves faster at the same temperature. At the same temperature, this gas will be moving slower than this because it's lighter, which makes sense. Lighter things are going to move faster at those lower temperatures because they take less, essentially they take less energy to move around. So as our weight gets lower, so we have less weight, so less mass, something has less mass, it's going to move faster. Or, like the problem said, in order of increasing molecular velocity.